Okay, so last time we started looking at atomistic mechanisms for diffusion, and we thought about interstitial mechanisms where you've got something like carbon in iron, which is what you have in steel, and the carbon atoms occupy interstitial sites in the crystal structure of the larger iron atoms, and they can jump between it, and as long as the concentration of carbon is reasonably low, you can work on the assumption that all of the neighbouring interstitial sites around a particular carbon atom are kind of empty. They're available to jump into. Today we're going to start by thinking about substitutional diffusion. That is where you've, let's say, for example, let's draw again some sort of cartoon 2D lattice like this. Let's imagine that I have one radioactive atom there, one radioisotope of the crystal that is going on, and you can see that around about this particular atom that's highlighted there, and obviously I could measure its diffusion by monitoring the activity. All of the sites that it would want to jump into, say its 4 nearest neighbour sites, they're all occupied. So it's not going to be able to do that. However, you can see that there is a vacant site over here, and so what's required is that essentially if this atom were to move into that vacant site and then that atom moved into there, then the atom can jump, and then maybe the atom behind it jumps again, and so on. And so you can see that our red atom has made one jump, but actually the vacant site is going to end up over here. The vacancy has done 1, 2, 3, 4, 5 jumps in the time actually that it's taken the red atom to do one jump. And so in a way you can see that the vacancies are very mobile. If you think about a vacancy as a thing rather than an absence of something else, like holes in semiconductors compared with electrons, you can see that actually the vacancies, because their concentration tends to be quite very low, the vacancies are highly mobile, and all of their neighbouring sites are usually available, because usually they're filled with atoms, and that's where a vacancy needs to go to jump. So you can see that this substitutional diffusion is really governed by actually the diffusion of vacancies. Now, some things from last time. If you remember, we'd say, so let's say the diffusivity of A, and the star is talking about, that means that's the case where I've, say, put a labelled A atom, like a radioisotope, in the thing, so I can monitor its individual diffusion. We saw that that was in general given by this expression. Remember, it was a sixth, which was a result for all cubic systems. You always have that. It was F was the correlation factor, which previously we'd typically take to be approximately 1, but is to do with whether in fact the atomic jumps do look like a random walk and that successive jumps are uncorrelated or not. Gamma was the jump rate, and L was the jump distance that it makes. And we saw that the jump rate depended upon the number of nearest neighbour sites, or at least the number of sites to jump to, some attempt frequency, so that was the number of sites, that is attempt frequency, and then a Boltzmann factor, due to the fact that you need to get over some migration energy barrier. So that was the free energy. Okay.
Actually, gamma is the frequency of what? Of successful substitution?
Yes, of successful jumps.
Of the latency?
No, at the moment of the A atom. Okay. That's what I've got there. Okay.
Which is a dark one.
Sorry?
Which is a dark one.
Which is a dark one, which is supposed to be red, but none of the colours show up properly. Okay. If we just look in 3D, let's draw an FCC. So here's a conventional unit cell of FCC, and I'll just draw as an open circle the face-centered atom there, and also on the bottom. So there is actually, hold on a minute. Okay, the open circles are the atoms that you can't quite see because they're hidden. If we imagine the atom that is on this front face here, this front face-centered atom, and I want that to jump to the position which is in the face center of that right-hand face, for example. And let's draw this. Okay. What I'm drawing in red there is I'm trying to highlight a plane, a 110 type plane in the FCC crystal. And can you see that the solid one here that's jumping is going to be this side of that plane, and the site that it's jumping to is the far side of that plane. Okay. Let me take that slice and draw it for you.
Is it going from one face to the other face?
Yeah. It's going between two face-centered sites. So it's going through that thing. If I try and draw that red okay, here are the four atoms at the corners of that red rectangle here. Okay, so these two are these two face-centered atoms, and these two are these two here. Okay, you can see that this has length. This distance here is a divided by root 2, whereas this distance here is a. Yeah. And then we ask ourselves, well, so what the jumping atom is trying to do is it is trying to jump through that hole, through that space. Yeah? And we can ask ourselves, what is the radius of that? Okay, so if R, again with our hard sphere atomic model that we looked at last time, we can see that again 4 lots of R amounts to a root 2. That's by looking along a face diagonal there, yeah, or by looking at the fact that 2R is a divided by root 2 along this direction here. Okay, everyone happy with that? So R is a root 2 at 4. But then looking at this particular diagonal, the diagonal of this rectangle, okay, looking along there, then you see that 2r plus 2r primed has got to be, well, the square root of a squared plus a half a squared, which is a times the square root of 3 over 2, and therefore r primed is the difference between those. I will let you do the algebra. It works out to be that times a, or actually sometimes it's more useful to put it in terms of the ratio of the, because this is now the same sort of atom wanting to jump, so we want it really in terms of the radius of the atom. It's that, which is about 3/4. Okay, so you can see there where the migration energy barrier comes from, because of clearly the distortion in the lattice that is going to be induced when the atom sort of tries to jump through there. Okay. Let's try and grab that.
I understood the connection between the two different diagrams. How the second one,
this one?
Yeah.
So this is supposed to be red. It is red, you just can't see it's red. This is red, and this is the same red as this red.
Okay.
So this is side A, because it's the height of the unit cell. And this is A over root 2, because it's half the face diagonal.
Which angle are you looking
And I'm looking at it straight on now, because I can see the red rectangle here. Okay. So I'm looking at it along, again, another 110 direction. So I'm looking at it full on. Yeah? So I've got those 4 atoms are the 4 atoms at the corners. And there's a space inside.
Which is, so the atom, the substitution is going...
So the atom that's jumping is going from in front of the board, where it sits nicely in a sight. Got to squeeze through that gap, which we've now shown is not quite big enough, to the far side. Okay? Good. Now, the number of sites, Z, this is the number of sites that are available for the atom to jump into. So Z now needs to be replaced by not just simply counting. With the interstitial diffusion, we simply just counted the sites because they were always all available. Now we have to take the number of sites but multiply by the probability that that site is vacant. Okay, in other words, the probability there is a vacancy on any particular site. Okay, and so what that means is that we want to actually, in gamma, let's keep Z as just the number according to the crystal structure, and then we multiply that by, essentially that probability is the mole fraction of vacancies, and then we've got the rest of it as before. Okay, so this is the mole fraction of vacancies, which is just equivalent to that probability that a given individual site is empty. And at equilibrium, the concentration of vacancies is going to depend upon the energy to create a vacancy, that is the energy to break all of the bonds between the atom you're removing and its neighbours, and also the entropy change. There's going to be a configurational entropy change when I put a vacancy in a crystal, because the entropy is going to increase. If I put one vacancy in, there's n sites that it can go on. If there are two vacancies, there's proportion to n squared sites, and so on. So it's actually rather similar to what we did for our binary AB alloy, particularly for the case where the mixing enthalpy was positive, where it cost energy to actually replace like bonds with bonds between two different species. But we're going to assume that actually the vacancy concentration is very much less than 1. If it isn't, then our material has probably fallen apart. Okay? That means I can ignore vacancy-vacancy interactions. Okay? And then I can write, I can just say that the enthalpy change that we get when we create a mole fraction X of vacancies is just X times the enthalpy change to create a mole of isolated vacancies. Yeah, that is a mole of vacancies that are so far away from the nearest other vacancy that there's no interaction between them elastically or in any other way. Okay, so if you like, this would be the way that you would calculate this. Is you're really asking yourself, if I just have a perfect crystal, I create a single vacancy in it, how much does that cost? And then multiply that by Avogadro's number. That would be the sort of way that you do it. Okay. In principle, of course, if you had a higher concentration of vacancies, then the vacancies start to interact, and then, of course, this energy is no longer proportional to X. It's going to have a different dependence. The entropy change, likewise, will be something to do with this is vibrational. Okay, so clearly if I go and remove an atom, that does something to the vibrational modes of the crystal. That has an impact on the entropy. But again, we're going to sort of assume that that's we're just taking isolated vacancies and looking at their contribution there. But there's also a configurational change, which is exactly the same as what we got for our binary alloy. So I'm not going to bother deriving that again. Everyone happy with that? Okay. It's just a number of ways of distributing a certain number of atoms and a certain number of vacancies over the total number of sites. So it's, instead of AB, you've now got A times vacancy, and instead of talking about the mole fraction of B, I'm talking about the mole fraction of vacancies. It's exactly the same calculation. Okay. So what does this mean? What this means is if I draw a graph now, I've got a linear contribution here, which is, so this is the free energy. So let's just write an expression. So the energy is going to, of a mole of this crystal with mole fraction X of vacancies, is going to be the free energy of just a perfect mole of A plus the change arising from introducing a mole fraction of vacancies delta G, which is GA plus XV delta HV minus XVT delta SV plus RT okay, all of that stuff. So there are two bits to it. If I'm talking about G here, here's GA for example, there's a bit which is proportional to X, linearly proportional to X. That results from the energy change and the vibrational energy change. And then there's another bit which is due to minus T times the entropy change configurationally. And remember what we said about what goes on here? This slope is vertically downwards, isn't it, at the left-hand edge? Because when you differentiate this function over here, the combination of logs, the derivative goes like 1 over xv. So the derivative diverges as you approach this left-hand edge. And that negative slope, remember in the case of, that's what always meant that you always got a bit of mixing in your binary alloy, close to perfect A and close to perfect B. The miscibility gap never filled the entire range of compositions because entropy always beat enthalpy in the dilute limits. And here you see that's going to happen again, and it's going to guarantee that there are always vacancies at any temperature above absolute zero. There have to be vacancies because entropy essentially demands that there are some. Okay. There's our expression. Okay, so if I want to find out how many vacancies are in there, I want to minimise the free energy with respect to the vacancy concentration. So that's going to give me delta HV minus T delta SV plus RT, taking the derivative of that expression gives me that. And I want that to be 0. Can you see this is just in here, log of x minus log of 1 minus x is just going to be the log of x divided by 1 minus x. So I'm going to get x over 1 minus x, and then it's going to be the exponential of everything else taken over to the right hand side. Okay, which is this, where of course delta GV, adjust those first two terms, but if I split it up, then actually there's a term that doesn't have sort of direct temperature dependence in there. There will of course still be some temperature dependence because the entropy will depend upon temperature, but it's sort of less strong, if you like, than it is in the case of the enthalpy term. Okay. The first term, the contribution from the entropy, is typically of order something like 3. Okay. The second term, this one here, well, delta HV is typically of the order of an EV per atom. okay, times, of course, Avogadro's number. Actually, sorry, we called Avogadro's number L, didn't we? Times Avogadro's number, okay, because that, strictly speaking, that's molar quantities in there. So that works out at about 100 kilojoules per mole. Which is, and this is typical, and this number, so this whole number is about 10 to the minus 17 at room temperature, but it increases to, say, 10 to the minus 3, 10 to the minus 4 at the melting point. Okay? So you've got a constant of order 1, and then you've got something that can vary by many orders of magnitude depending upon temperature. Clearly this is the thing that is really dominating what is going on. And if we assume that xv is much less than 1, then obviously the denominator we can just approximate by 1, and therefore xv looks like just e to the minus delta gv over RT. Okay. Now, let's go back to here. Pop that in there. So gamma is now z times nu times the exponential of delta G migration plus delta G vacancy over RT. Okay? So it's still of the same form that we saw for interstitial diffusion. Some sort of prefactor, and then this Arrhenius, this Boltzmann type exponential dependence. But now, the activation energy, Q, includes the free energy of formation of the vacancy. Okay? As well as the migration energy. Is that okay? So in other words, the diffusion process isn't going to look qualitatively any different, except for the fact that it will just seem to have a much higher activation energy, and therefore it will tend to be much slower at a given temperature than an interstitial mechanism. Right. Here's an interesting thing. Within a given, if I have various materials, and I select from those materials which have the same crystal structure and the same type of bonding. So, you know, I'm looking at FCC metals, for example, or tetrahedrally networked semiconductors, on the other hand, right? That's what I'm sort of talking about. Then Q over KB times the melting temperature is constant, okay? So that's the melting temp, and I'll put if same crystal structure and bonding type. Okay, and that constant, for example, is about 18 for if we take the example of close packed metals, just for example. Okay. Do you understand why that is?
It's more difficult to diffuse upon this strong and also melting temperature is directly related to the strength of the bond.
Exactly. Okay, the things that contribute to Q, vacancy formation energies, migration energies, are directly dependent on the strength of the bonds between atoms, as is the melting temperature. So in other words, it's just a proportionality relationship. In our now, D0 will be constant across those things. Remember, D0, yeah.
So does that say constant?
Yeah, the constant is about equal 18. Yeah. Now D0 is a constant, isn't it? D0 contains the number of nearest neighbour sites in the crystal structure. We said the crystal structure is the same here. And it depends upon the attempt frequency. So it's kind of assuming that phonon frequencies are comparable in materials with the same crystal structure and the same bonding type, which is not unreasonable. But if we take D0 is constant, then that tells us that the diffusivity at the melting temperature is also a constant, typically of the order of 1 micron squared per second. Okay, and therefore D of T divided by Tm is constant over this series of materials. Is that okay? Because D is D naught e to the minus q over kBt, but we've said that that is D0 e to the minus q is a constant times Tm, constant times Tm over T. Is that okay? So for the same value, so in other words, but in this series of selected materials, D0 is a constant, this is a constant. So for the same value, for the same ratio of temperature divided by melting temperature, you will get the same value of D. Okay? So this is sometimes called homologous temperature. And essentially what it says is if you measure temperature on a scale relative to melting temperature, then materials within these classes, the diffusion is exactly the same. It proceeds at the same rate. Okay. So, if you were to take experimental results of diffusivity against temperature for all these materials, but then you were to scale the temperature axis by dividing by the melting temperature, then you expect the lines to come and sit all on top of one another. Okay. And that's pretty good. Let's look at the effect of temperature again. So, I'm going to take an example of copper. Copper has a melting temperature of just over 1,000 degrees Celsius. It has a value of D0, which is this, and it has a value of Q, which is just over 2 eV. So at 800 degrees Celsius, at a reasonable temperature, we plug all of this in, and we will get that D is approximately 5.4 times 10 to the minus 15 meters squared per second. Okay, and what does that mean? that means that after 1 hour, square root dt, our characteristic diffusion length, is about 4 microns. Decent distance. Okay. Now, I also know that in copper, the jump rate is 2.5 angstroms. Sorry, the jump distance is 2.5 angstroms. Someone asked me we asked before, didn't we, how do you get the jump frequency? And I said, you know the diffusivity, you know the jump distance, and therefore you can work it out. So the jump rate is 5 times 10 to the 5 per second. And of course, it's a close packed metal, so Z is 12. At 20 degrees C, gamma then has dropped to that. Okay, are you happy about how I'm going here? I know I know these values. I know the diffusivity. I can then work out from my equations what gamma is. Here is the gamma at 20 degrees C, room temperature. That is 1 jump per 10 to the 12 years. Okay? The universe is 10 to the 10 years old. Okay? So that tells you that that basically observing diffusion in copper at room temperature is not a productive use of your life. If you're just going to sit there and stare at a single copper atom. Of course, the saving grace is that a decent sample of copper has got multiple Avogadro's numbers, 10 to the 23 of atoms. So actually, even at this minuscule jump rate, there's still going to be hundreds of jumps per second occurring within a molar sample of copper. But, that's proportionately extremely low. So diffusion is essentially switched off. But you can see the massively dramatic difference that temperature makes there, between being at room temperature and then going up close to the melting temperature. Okay. So I mentioned at the beginning that jumping of atoms we can consider equivalent to jumping of vacancies, like holes in semiconductors. And that vacancy diffusion is like interstitial diffusion, because you can generally assume that all of the sites are available for a vacancy to jump into. So what does that mean? Just to write something down here. So the diffusivity of vacancies is going to be a sixth of gamma L squared. So let's write the sixth L squared. Then let's write gamma down. There's an entropy change of migration. There's an enthalpy change of migration, okay, which is dA over xv. In other words, remember the mole fraction of vacancies was what we put into the diffusivity of atoms to take into account the fact that there had to be a vacancy on the site for it to be available. But for the vacancies, all sites are available, so that factor of x is absent there, which just means that the diffusivity of vacancies is the diffusivity of A atoms divided by the mole fraction of vacancies. We said the mole fraction of vacancies we're assuming to be much less than 1. Therefore, as you'd expect, the vacancies diffuse much more rapidly than A atoms. All right. Okay. Now, I'm going to come to a topic that we haven't got... Yeah, great question.
The diffusion of vacancies should be more or less like the diffusion of atoms, more or less like electrons and holes, right? So you can think of a vacancy diffusing in one direction and the atom diffusing in the other.
Yes.
So the fact that they are not the same, or there are many orders of magnitude,
Yes.
depends on the fact that you are focusing on that specific atom to jump, and not on any atom to jump.
Yeah, because I'm focusing on a specific atom, exactly. Back to this cartoon at the beginning. If you think about the beginning and end of that process, the vacancy has jumped a decent distance, but actually the majority of the atoms have not moved at all.
Okay, so actually you are thinking about an impurity diffusing.
I'm thinking particularly about that. That's the star is quite important there, as you say. That is, pick one atom and ask how that diffuses through the material, not think about how all of the atoms collectively may go, because for actual transport of matter, I need one particular atom to have gone from here to over there. It's no good if a whole load of other atoms have moved around, but actually they haven't contributed anything to where stuff has gone. Okay.
So do we need to start the final equation? The
Yeah, probably be a good idea. Let me just talk about. Let's just go. Yeah, so let's pick up on that a little bit. As I say, I haven't got time to do all of this now. But if we now go back to our binary AB alloy, and now we want to consider, because remember, this is what the thing that we've always set out to understand in a way, is how does the mixing occur in this system? So we know that, assuming we're not in the miscibility gap here, assuming mixing is actually going to occur, we know the A atoms want to go into B. So there's going to be a flux of A atoms into B, and there's going to be a flux of B atoms into A. But the diffusivity of A and B atoms is not the same. They may have different sizes, different migration energies. So I've drawn the case where A atoms diffuse more rapidly than B atoms. So what happens? What happens in this situation? You've got this thing on your desk. Heated it up. Diffusion is happening. A atoms are going over to the right hand side. B atoms going over to the left hand side. But the rates are not the same.
Positive atoms would be very different.
I'm assuming the same crystal structure as we have all the way through. So there's one,
So atoms are going to mix within the same structure. Still have the same.
They've got the same lattice, they sit on the same sites. So A and B compete for the same sites, which is what we always have before. Yeah, so it's not interstitial. The energy, we can assume here A and B are similar size, so the energy to put a B atom into an interstitial site of an A crystal is just too high to contemplate. It's not going to happen. So we know something else about this now. There's something else in here. Yeah?
There'd be more vacancies on the A side.
Okay, right. So we now know there must also be vacancies. At finite temperature, there have to be vacancies in here. And a jolly good job too. Because for the A atoms, this is substitutional diffusion we're talking about in our picture that we've always used here. So for the A atoms to go to the right, the vacancies must be coming to the left. And so also for the B. So in other words, the fact that the A atoms they must be leaving empty sites behind that are not being filled by B atoms coming the other way. In other words, there must also be a net flux of vacancies from the right to the left. Yeah? What does that mean? Does that sound okay? or are you worried about anything? Let's leave it for a long time.
There will be more atoms.
Okay, there's clearly going to be more atoms on one side than the other. There's going to be more atoms ending up on the right-hand side than the left-hand side. Does that worry you?
We should disappear at some point.
Sorry?
We should disappear at some point.
You want them to disappear at some point?
No, I mean, it would disappear if it went on.
Well, it wouldn't disappear, but I mean, no matter has been created or destroyed here. I'm not losing any atoms here. So nothing can disappear. It's moved.
At some point it will be so in the left hand side there will be so many vacancies that it's very likely for atoms to so simply diffusion and the right hand side becomes much less likely because there will be less vacancies.
Okay, so we're getting to two of the points here. One of the points is about the thing moving. Can you see that it looks like the sample is going to translate, doesn't it? Its centre of mass has moved. Yeah.
If you leave it for long enough, then it's going to be the longer time scale comparatively the short difference with diffusivities. That will mean it will eventually be alright.
No, tend the sand of reach. No, I don't think it's not quite. Well, we'll see. We'll be able. Next lecture, we'll be able to assess whether that's correct or not.
You're assuming that JA and JB are independent of the number of vacancies. So if you have more vacancies at the beginning, that means it's easier for A atoms to migrate to the right-hand side because of these vacancies. Once these vacancies have moved to the left, you don't have these vacancies for atoms to migrate.
Yeah, but you see, I'm leaving this for a long time at a reasonably high temperature, so you expect thermodynamics to you expect the system to be roughly in equilibrium, and we showed that in equilibrium there's a population of vacancies. So you can't scrub vacancies that easily. Okay, we're getting to two things. One is, well, does the sample move? Because then that would violate all sorts of things, wouldn't it? The centre of mass of that moves, and you started out in the zero momentum frame, and now the thing all suddenly seems to have sort of some finite momentum. That can't be right. So there must be something wrong with this picture. Okay, because otherwise you'd be able to, for example, you put it on the slight slope, couldn't you? Put the sample on the slight slope, heat it up. And with the random motion of the heat, you might be able to get the sample to creep up the slope, and then we've got some energy that you could then extract, and then, hey, we've broken all sorts of rules of thermodynamics, haven't you? So we need to think carefully about that. The other thing is we're going to need some sources or sinks of vacancies. We're going to need some places where vacancies can be created on the right-hand side and destroyed on the left-hand side. Okay. In order for this to, otherwise, as you say, leave it for long enough and you'll fill up all the vacancies. You would fill up all the vacancy sites on the left and there'd be none left on the right. That's not realistic. That's not what really happens. It must actually be the case that within real materials there are always sources and sinks of vacancies, places where, although we talked about that vacancy formation energy being of the order of 1 eV per atom, we need some places in these things where it's much less than that. Okay, so I think that's enough